All right, in today's lesson here, we're going to be taking a look at projection vectors, just geometric transformations, just going through some examples here. So let's take a look at our first question here. We have a function going from R2 to R2 such that it's rotating this vector, x1, x2. We're going to rotate this vector by an angle of pi over 6. So the first thing we want to look at is recall that your matrix, your rotation matrix, is cos theta sine theta, negative sine theta cos theta. And if you recall, that's discovered by taking the image of your standard basis vectors, so 1, 0, and 0, 1, and then examining their outputs. If it's rotated, in this case, by an angle theta, you discover that this is our rotation matrix. So in this example here, they want this to be pi over 6. So the matrix that we're interested in evaluating is going to be cos of pi over 6, sine of pi over 6, negative sine of pi over 6, and cos of pi over 6. Computing this and simplifying this, we get, all right, going ahead and computing this here, I end up getting here root 3 over 2 minus a half and 1/2 and root 3 over 2. So this is the matrix such that it'll rotate any given vector by an angle of pi over 6 or 30 degrees. Let's take a look at another example. All right, looking at our next example here, again, we're going from R2 to R2, and what we want to do this time is we want to do a rotation by an angle of pi over 2, followed by a reflection in the x2 axis here. So let's go ahead first and create our matrix to represent a rotation of pi over 2. So again, like discussed, this is going to be cos of theta, sine theta, negative sine theta, cos theta. That's our standard rotation matrix. And we're going to evaluate this at pi over 2. So this is going to be cos of pi over 2, sine of pi over 2, and negative sine of pi over 2, and cos of pi over 2. And evaluating this here, we end up getting here cos of pi over 2 is going to be 0. Sine is going to be -1, or negative sine of pi over 2 is -1, 1, and 0. So we go ahead and have my rotation matrix here. So that's our first matrix that we're going to apply. Now, after that, it looks like it's a reflection in the x2 axis. So if you take a look here, we've got our Cartesian plane here. This is x1, this is x2. To find your rotation matrix for this one, again, let the operation go on 1, 0 first. So if I'm going to take the image on 1, 0, suppose this is my vector here, 1, 0, and we want to reflect this in the line x2. So if I'm reflecting this in the line x2, it's going to go the opposite side here, and that's going to be -1 and 0. So I know that this is the output value is going to be -1 and 0. Then we're going to take a look and look at f at 0, 1. So if I go to examine f at 0, 1 here, let's erase this here. If I go to examine f at 0, 1, we're going to be up here now. And this is f at 0, 1. If I reflect this in line x equals 2, it's not moving. So it outputs just itself in this case. So this is going to be 0, 1. So therefore, the rotation matrix, the geometric matrix here to reflect in the line x2 is going to be, this is our column method discussed. So this is going to be -1, 0, and 0, 1. So putting these two together, to find the combined rotation matrix, I have to first take this matrix here and multiply by this matrix here. Let's go ahead and do that. All right, so now that we have our two matrices here, we have to watch out. I just wanted to make note of this. Now, to compose this together and create the matrix that's going to first rotate this 90 degrees or pi over 2 and then reflect this in the x2 axis. Notice if I would have written If I go ahead and write it this way, this would be incorrect. If I put this matrix down and then this matrix down, when your vector, in this case x1, x2, acts on this, you're going to actually do this operation first, which would be my reflection in the x2 axis. So if you're going to create your matrix that's going to first rotate and then go ahead and do the reflection in the x2 axis, we have to flip the order of this. So the order should go like this, and then multiplying this out here, I end up getting here 0, 1, 1, and 0. So this is the matrix that's going to go ahead and do a 90-degree rotation on that vector and then reflect that in the x2 axis. All right, let's take a look at another example. All right, let's take a look at another example here. So in this example here, we've got a bunch of geometric transformations we want to do. We want to first do a rotation by an angle of pi over 2. That's going to happen in the x1, x3 plane. After that, we're going to do a reflection in the x1, x2 plane. And then lastly, do a stretch by a factor of 5 in the x3 direction. So let's go ahead and do that here. Let's first draw our plane here. So let's go ahead and do a quick sketch here. So I'm going to label this. This is going to be x1, x2, x3. And as I take a look here, first thing I want to do is I want to rotate this 90 degrees. So go ahead and examine what happens when I apply this to the vector 1, 0, 0. Again, using your right-hand rule here, you'll see positive orientation is going to be going in this direction. So if I go ahead and rotate this 90 degrees, again, the rotation is happening in the x1, x3 plane. If I rotate this 90 degrees, this vector is going to move to here, and that's going to be the vector 0, 0, -1. So that's going to be the first column of our rotation matrix. All right, now let's take a look at the vector 0, 1, 0. It's going to be somewhere about here. And again, you're rotating in the x1, x3 plane, so that's completely unchanged. And now we're going to go ahead and take a look at the vector 0, 0, 1. So the vector 0, 0, 1, it's going to be somewhere here. And again, we're going to be rotating this 90 degrees. And again, we've figured out our orientation here, and we know the direction. So I know that positive orientation is going to go in this way. So 90 degrees is going to map me to 1, 0, 0. Okay, continuing on here, we now want to do a reflection in the xy plane. So in this case here by xy, let's go ahead and graph this again. So this is our first rotation matrix right here. And then I want to do a reflection in the x1, x2 plane. So again, if you take a look at this here, take a look at our standard basis vector. So look at 1, 0, 0. If I reflect this in the x1, x2 plane, it will be unchanged. So right away, I know my first vector will be 1, 0, 0. If you take a look at 0, 1, 0, same thing, that will also be unchanged. And lastly, the vector that is affected, though, will be taking a look at this vector here. This is the vector 0, 0, 1. If you reflect this in the x1, x2 plane, it's actually going to go in the opposite direction, straight down, and this is going to be 0, 0, -1. So that'll be the third column for us here, and this is going to represent reflection. So this is a reflection in the x1, x2 plane. This is a pi over 2 rotation, and that's in the x1, x3 plane. And lastly, we have a stretch by a factor of 5 in the x3 plane. So again, if you draw yourself a little diagram if you need to, this is x1, x2, x3, and you got your plane here. So again, taking a look here, if you take a look at the vector 1, 0, 0, if you stretch this by a factor of 5 in the x3 plane, nothing will happen. So again, if I write down my transformation matrix, it's unchanged. The same thing will happen for 0, 1, 0, right? It has its third coordinate is 0, so nothing's going to happen for that one. However, if I take a look at the vector 0, 0, 1 and stretch it by a factor of 5 in the x3 coordinate, it's going to go ahead and be stretched in that direction. So this will give us 0, 0, 5. And this is our geometric matrix that's going to represent a stretch by a factor of 5. So again, the order matters here. We want to first apply this matrix, then we want to apply this matrix, and lastly, then we want to apply this matrix to a given vector that you get. So we have to put that in that order when we multiply these out. Let's go ahead and do that. So I'll go ahead and putting these in order here. You can see I have my rotation. Then after the rotation, I have a reflection, and then I have a stretch. So multiplying this all out, we get the following. So going ahead here and multiplying this out, we're going to get 0, 0, 0, 1, 0, 1, 0, and lastly 1, 0, 0. And then multiplying this out here, we get 0, 0, 1, 0, 1, 0, and then the last row, it becomes 5, 0, 0. So we are finally done. This is the matrix that's going to do a rotation of 90 degrees, reflection in the x1, x2 plane, and then a stretch by a factor of 5.